Hey guys, today let's talk about kinematics. Kinematics, real simply, is the study of motion, how things move, where is something, when is it going to get from here to there, how fast is it moving. We could be talking about cars or bicycles or airplanes. We could be talking about an electron going around the nucleus of an atom. We could be talking about galaxies moving away from each other. The same rules apply, and that's kind of neat. There are 5 variables that I want you to keep in mind. You can see them here. We've got the displacement. That would be the distance that something travels. It's actually how far something ends up from where it began. So we could draw a little car here, and you get in your car. Hope your car looks better than that. And you go over here. You can see that you've moved some distance, some displacement. We measure that with x. V naught, or V sub 0, the velocity at time 0. How fast am I moving at the beginning of the problem here? And V would be the final velocity. Over here I reach some other speed, V. The A stands for the acceleration. I'm speeding up that whole way, and so I usually draw that up here on top. And the T is how long it takes to get there. So we start at time 0. Maybe it takes 4 seconds to get over here, right? Maybe we started moving at 2 meters per second and we ended up going 10 meters per second, all right? And maybe we know the acceleration is 1 meter per second squared or something like that. Whatever the numbers are, we put them in and we see what comes of it, all right? There are 3 little formulas that tie these together. And here, these make sense if you think about them. The final velocity is going to be the initial velocity plus any extra velocity that we got because of time and accelerating. If I'm accelerating for a period of time, that's going to make me go faster. And if I add that extra velocity to the initial velocity, I should have the final velocity right there. A similar thing happens right here with displacement. When I travel at a speed for some period of time, that's going to move me down the road some distance. If I'm accelerating, that's going to give me some extra distance. If I speed up, then I'm going to travel farther than if I don't speed up. So I've got to add this extra distance because of the acceleration over that same period of time. So that's a nice little formula. And then right here I've got v squared, the final velocity squared, equals the initial velocity squared, plus 2 times the acceleration times the displacement. That one's a little bit harder to get your head around, but it comes from mashing these two up with algebra, taking these two and pushing them together into a single formula, and the time can drop out and stuff. All right, those are the 3 formulas. Let me show you real quick how to use those. When we get a problem in physics, it's going to look something like these. It's going to be a word problem, and let me see if I can get this out of your way here. Well, it's got to go somewhere. A car is at rest when it accelerates at 4 meters per second squared for 3 seconds. Find x. And you know what? The easiest thing to do here, what I would like you to always do, is just go through and circle all the numbers. A car at rest, that's actually a number. That's the initial velocity equals 0. At the beginning of the problem, I'm at rest. I'm not moving. My speed is 0. It accelerates at 4 meters per second squared. So I'm going to circle that number. I need to figure out what it is. I've only got 5 choices. I've already used V naught. So could it be the final velocity? Well, it's in meters per second squared. The only thing in meters per second squared is the acceleration. So it's got to be this guy right there. And then I've got a 3 seconds. Clearly that's going to measure the time. And we're looking for x. All right, that's all you're trying to do. You read this little story, and they're going to give you some numbers. With these basic kinematic problems, it's always 4 numbers. They give you 3, 1, 2, 3. They're asking for a 4th one. Your job is to come down here to your list of formulas and say, well, I got 3 formulas that tie these 5 variables together. Wonder which one I need to use. And, you know, if you don't know, you can just start at the top. And you say, well, let's see, I've got V naught. I've got A, I've got T. Can I get X out of that? Oh, wait, X isn't even in that formula. I could solve this thing mathematically, but it's going to give me the final velocity. I want the displacement. So that's not the one that I want to use. Checking the next one. I've got V naught, I've got T, I've got A, I've got T, and X is the variable that I'm looking for. That's the formula that we want. When you can find one of these where you either have or want to know all of the variables involved, that's the right formula. And I would encourage you just to go ahead and jot it down. If you'll always start by writing down the formula, then everybody on the planet can see where you started from and know your thought process. Just for kicks here, let's see what would happen if we tried to use the last one. I've got V naught, so I'm going to check that one off. I've got the acceleration. I want to find the X, so that's a question mark, but I don't have the final velocity. That's a question mark. See how there's two question marks in that one? There's two unknown variables. You can't solve an equation that has two unknown variables. So that one's no good. I can't even, the math doesn't even work on that. Now I could come up here on this first equation, solve this one for V, and then bring that down here. But see how the second one does it in one step instead of doing this and then that, the two steps? So the easiest way is just to grab that second formula and run with it. All right? And when I say run with it, oh, you know what? I should have written it up top too. I don't know if I can move this thing or not. Let's see if it, nah. Oh, man. All right. So I'm going to write it up here on the problem we're actually working on. And here it is again. X equals V naught T plus 1/2 AT squared. All right. This is already solved for the variable that I want to know. And all I have to do is to fill in the numbers. It was at rest. V naught equals 0. So I put that in. The time is 3 seconds. I've got plus 1/2. The acceleration is 4 meters per second squared. The time is 3 seconds. That has to be squared. Make sure that you keep up with all those exponents and all the little details of where people get lost on this thing. There's nothing hard about physics, but there's a lot of little details that you got to pay attention to. 0 times 3 is 0, so that goes away. Right here, 3 squared would be 9. 9 times 4 is 36. Half of 36 would be 18. And if you watch the units, and this is another thing I would encourage you to do, see how right here I've got a meter per second times the second. The second on the top is going to cancel the second on the bottom, nothing but meters. I can do the same thing right here. I've got a second squared on top, second squared on the bottom. That's going to cancel nothing but meters. So the answer here comes out in meters. That makes me feel good because I'm looking for an X. I know that X has to get measured in meters, so that feels pretty good, and that's the right answer there. Now we could also do that on the calculator, and it's important to know how to talk to your calculator. Here I could go 0 times 3 plus, I'm going to use a 0.5 for the 1/2. The decimal version is easier to put into the calculator than the fraction, and put in the rest of that. Here's the squared button right there. So I've got all that, and sure enough I get 18. If you want to forget about the first term, you could just go 0.5 times 4 times 3 squared, and let that first term drop off. I get the 18 that way, whatever. But just do it like it says. Now, here's a second one, so let's give this one a try. I got a cat moving it. Here's a number. Here's a number. Comes to a stop. That'd be the final velocity equals 0. Here's a number, 4 meters. Meters measures displacement. Find the acceleration. A equals question mark. And we said this was the initial velocity. Okay? So again, you see how there's 4 numbers there? I got to have 4 numbers. 1, 2, 3, 4. 1, 2, 3, 4. And I've already got the T. 1, 2, 3, 4. They're going to give you 3 numbers. Ask for the 4th one. That's the whole game. I already had this written here. Let's see if this one will work for us. I do have the initial velocity. I don't have the time. And I'm looking for A, so I don't have that. That's 2 unknowns. Okay? I can't use that equation because it's got two unknowns and it's mathematically impossible to solve it. So I don't want this guy. What else could I do? Well, V naught V X A. That doesn't have an X. V naught V X A. Huh, there's those same four ones. That's the equation I want. V squared equals V naught squared plus 2AX. It's a little matching game. You can do this. Just find the numbers, figure out what they are, find a formula with those same variables in it. It'll work every time. Now, this guy, I'm looking for A. And A is right here. Now up here, when I did it, remember I was looking for X and it was right up front and everything else was on the other side. It was already solved for the right variable. This one's not. So we need to do a little bit of algebra to get this in the right form before we put numbers in. And just to kind of help you think about this, some people don't like working with these letters instead of numbers. Here, I don't know where to go with this and not use up all my space. Let me make up a second problem that, like if I had 10 equals 4 plus 2a, something like that, we could do that all day long, right? I'm going to subtract the 4. 10 minus 4 is 6, and that's 2a. Okay, now I'm going to divide by the 2. A equals 6 divided by 2, which would be 3, right? Easy peasy. This is the same problem. Okay, I've got some stuff right here that is added to what I want to extract. So if I just subtract v naught squared, just like we subtracted 4 up here, then that would get me back to the point of v squared minus v naught squared. This would cancel on the right, and nothing but 2ax over there. And then remember how we divided by 2 here on both sides? I'd have to do that. I'm going to come in and divide by 2 here. Dividing by 2 will cancel, but I got to do it on both sides. I'd also like to get rid of that x, which is also multiplied, so the opposite would be division. And if I do it on the right and do it on the left, that should be fine. So I end up with v squared minus v naught squared over 2x, and that's what I want to put my numbers into. Okay, now you can put the numbers in first if you want, but I'm going to tell you right now, you're going to have to do the same algebra, and it's going to be a whole lot more writing, because now I've got to put 2 meters per second squared, and that's going to, you know, so there's a lot more going on. And if you can learn to do this with just the variable names, it makes life so much easier. It's also true here for every problem, right? We haven't made any assumptions about the numbers we're going to put in here. So I would encourage you to do that. One more word of caution here. This is subtraction, that's division. Division is more powerful than subtraction. If you remember the please excuse my dear Aunt Sally thing, we had to do our parentheses first, exponents second. I do have some exponents here. Multiplication and division third, so that would suggest do this first, but I need all of that to stay together. So wrap this up in some parentheses, and then that's that first step right there. You got to do the exponents inside, and then you can do the multiplication division with that 2x that's on the bottom. I'm going to go ahead and put the numbers in. We'll get the calculator back out and see what this comes up to. There's that open parenthesis. I'm looking at a v squared. V was 0, so here's 0 squared minus v naught. V naught is 2 meters per second. That has to get squared. Put some extra parentheses around there to make sure that the number and the unit gets squared. Downstairs I've got a 2 and I've got an x. My x was 4 meters. And all together that's going to be a. All right. So right here's a good place to get the calculator back out. You could do this by, just by hand, but I'm going to put that opening parenthesis, 0 squared minus 2 squared, close up the numerator, that's my top. And then downstairs I want to do divide by 2 and also divide by 4. So if I divide by 2 and also divide by 4, that gives me negative 0.5. Now if you don't like that divided by, your choice would be to wrap some parentheses around the bottom and call it a multiplication. That would look like this: 0 squared minus 4 squared. I'm sorry, 2 squared. Let me get the right number in there. 2 squared divided by parenthesis 2 times 4. Okay, that'll work as well. Gives you the same answer. That's fine. I usually like to go this top way just because it's less writing. It's quicker, easier, lazier. Okay. What you don't want to do though is go 0 squared minus 2 squared for the top and then divide by 2 times 4. That will goof you up big time. Okay, so don't do that. Pick one of those first two ways there. All right, we got a negative 0.5 for our answer. It's always good to go through and say, does that make sense? And, you know, just question everything. That's kind of the point of science. What do we know? How do we know it? Can we show it to be true? Well, this negative means that it has a negative acceleration. It means we're slowing down. And indeed, when we look back at the cat problem, we are slowing down, right? It was going 2 meters per second. It came to a stop. All right. The meters per second are the units that this should come out in. So it's worthwhile in my book to take a moment here and say I've got meters per second, which gets squared. So that's going to be meters squared over second squared. And then that's all divided by these meters on the bottom. That's a compound fraction. I'm going to write it like this for a second. And then I could take that apart, invert and multiply. Take the bottom fraction, flip it over like that. You can see that a meter here on the bottom is going to cancel 1, but not both of those on the top. So I'm left with meter per second squared. That's the unit. The unit checked out. That means our algebra checks out. We put the numbers in. Doesn't mean that we hit all the buttons right on the calculator, but we're in the right ballpark, right? This is looking good. So, but that's the right answer there. We're slowing down at 0.5 meters per second squared right there. These accelerations are interesting right here. This unit really means that every second I'm going 0.5 meters per second slower here, because I'm negative, than I was the second before. Acceleration says how many meters per second faster or slower are you going than the second before, and that's what we use to measure that. We just write it meters per second squared for to make life easy. Okay. Now, kinematics also deals with that was all one-dimensional kinematics. All the you know, a train going across Kansas, apple falls from a tree. All of those kind of problems are fine. What if we have things happening in 2 dimensions at the same time? When I throw this rock off of a cliff over here, it's moving to the right and it's up. A little bit later on, it's going to be here and it's moving to the right. It's stopped going up because gravity's pulling down on it, but it hasn't started going down yet. A little bit later on, it's moving to the right and down. So see how there's 2 dimensions in these things? I call this one a cliff problem because it's up here and it's going to fall off of this cliff. Maybe we shoot a cannon off of Fort Wall. Maybe we jump off of a roof into a swimming pool. Maybe, you know, there's a car that drives off a cliff for a movie or something. Whatever. There's 2 dimensions, and as such, we need to separate those 2 dimensions into the x and the y directions. Instead of having a single list of variables, we really need 2 of those. And to say, what's the displacement in the x direction? What's the initial velocity in the x direction as opposed to the initial velocity in the y direction? What's the acceleration in x versus acceleration in y? This time is going to be the same number right there. So that kind of works in our favor, but everything else is going to be independent. It doesn't have anything to do with the other one. So when we do these cliff problems, usually we're going to have to use the y direction and find time. How long did it take for this thing to fall straight down off of the cliff? Okay, that would be my y direction stuff. And then at the same time, this rock is moving in the x direction. And we need to think about that. So you're really doing kinematics twice. And when you put it together, it gives you the true path and the time in the air and how far that thing goes and all those kind of problems. Here is an example of that. And what I'll do is circle the numbers. And I actually left a number off of this. That 13 meters is the height of the cliff. I'm going to add right here at 6 meters per second. I forgot to type that part in, sorry. So let me draw a little picture. Pictures are invaluable here because it kind of flips it over into the other part of our brain that sees things, that makes it real. And so if you just come in here and draw a little picture and say, well, I've got a rock at the top of this cliff, and I'm going to throw it horizontally. So I'm picturing this rock that's moving this way, and I know that gravity is going to speed that thing up as it falls. So it's going to make a path something like that. All right? That trajectory, that curved path right there is going to look something like that. It, at every point, is still moving to the right, but it's speeding up faster and faster the farther it goes. So it puts that curve on the line like that. Remember how we said we're going to work in the y direction and find time? Let's go ahead and do that. I need to get all of my y direction variables. This is a y direction variable because that's the height of the cliff. It starts at the top, it ends up 13 meters down below. So right here for y, I'm going to put 13 meters, and to represent that down, I'm going to put a negative sign right there. We create this thing called a coordinate system. You just kind of draw a line, say everything that points up, I'm going to call it positive. Everything that points down, I'm going to call it negative. All right? Now you could name it the other way, negative up, positive down if you wanted to, but most people are comfortable with this, so I'm going to stick with that. I need to know the initial velocity in the y direction. Well, there's not any. When I threw it, it was going sideways. It was horizontal. So the initial velocity in the y direction is 0, and I don't have to worry about that. The final velocity we're not going to worry about here in either the x or the y direction. You can pull it back up if you need it. You know, if they say how fast was it going when it hit the ground, it's there and you could get it, big deal, but I'm going to ignore that one. The acceleration, this is gravity right here. When we're on Earth, and presumably this rock is thrown on Earth, they didn't tell me it wasn't, we use the number 9.8 meters per second squared. That is the acceleration due to gravity. And that gravitational pull is downwards. The acceleration is down. Remember how down was negative? So this guy needs a negative sign too. And we're trying to find time. 1, 2, 3, 4 variables. We're good to go. I've got my 3 formulas. These are really configured to work in the x direction. And sometimes you'll even see people put little name tags on these things to make sure that all the variables are x direction variables. Kind of like when you go to a convention and they slap a name tag on you that says, hello, my name is Bob. This is, hello, my direction is x. All right. What we want to do is to have a second copy of these in the y direction. Those formulas work in the x direction, they work in the y direction, they'll work in any direction. But here, if I purposely create a second copy that is specifically for the y direction, it kind of helps keep things straight here. So that's the formula that I want to use right there. I'm going to bring it up here. I should have just written it up there. Y equals V naught y t plus 1/2 a sub y. See what I'm talking about with that subscript there? It's a little bitty one. It's not a full-size y. I'm not multiplying by the y displacement here or anything. It's just a name tag on that thing. All right? So there's what I've got. And I'm looking back at my numbers over here, and I go, ooh, I got a 0. That simplifies things. When the initial velocity in the y direction is 0, 0 times t is going to be 0, so I get to cross that whole term out, and that makes the math a little bit easier, actually a whole lot easier. At this point, I want to get that t by itself, so I need to get rid of the 1/2. If I were to multiply this side by 2, 2 times 1/2, 2 on top, 2 on the bottom are going to cancel. But if I do it on one side, I got to do it to the other side. I'd like to get rid of that a sub y. That's multiplied, so the opposite would be division. Set it up so those cancel, but don't forget to do it on the other side. Looks like that. Might as well write and see where we are. At this point, I've got a 2y over a sub y. You could call that g if you wanted to for gravitational acceleration. I'm going to just leave it a sub y because that's what we've got it recorded as over here, but whatever. And then that's t squared. I don't want t squared, I want t. So the last thing that I need to do here before I put in my numbers would be take the square root of the right side and let that square root and the squared cancel each other out, and I just get t. But then again, if it's on the right, I got to do it on the left. Got to keep this thing balanced up. And we'll put our numbers into that and get the time. So here we go. 2 times the y, that was a negative 13. And the acceleration in the y direction is negative 9.8. Like that. And that's going to be how long this thing spent in the air. So let's see what that is. I'm going to come in here and go square root 2 times negative 13 divided by negative 9.8. Okay. You can see all those negatives at work there. If you get a positive, I mean, if you leave one of them out, then weird things are going to happen. And just so that you know what I'm talking about, let me do that. I'm going to pull this back up. If I forget this negative sign right there and hit enter, see how it gets mad at me? Okay, so if you see that, that's a reminder, hey, I goofed up my coordinate system. I need to try that again. All right, and put that back in there. And it should come up a positive time. All right. That number, I went ahead and put down all of these digits, and we've talked about this a little bit before in the math review video, but I just want to remind you here that normally in science we would cut that way down, right? We might not do it on this step. We might wait to the next one, but this had 2 significant digits. This has 2, or you could say, well, that's a accepted number, not a measured number. So, but you know, normally we'd say let's round this to 2 significant digits. This is less than 5, so I'm not going to round up. I'll just leave it at 1.6 seconds. And normally that's the answer that we would put. However, we're putting these into D2L. It's thinking like a calculator. It calculates the number and it gets this, and then it gives you 5% up or down from that. So, you know, anything up to 1.7 and down to maybe 1.5 would be fine, okay, if it were looking for the time. The 1.6 would work here, okay? But you can see how, no, actually it wouldn't. If I go, let's see, not that number, this number, there's the answer, times 0.95, 95%, 1.54, yeah, it'd still be all right, okay? But sometimes as that number gets smaller and smaller, you'll miss by rounding too much. Short advice here, always put more decimal places into the computer than you think you need, you know, just put a couple extra, it doesn't take any time. Here I'd probably go 1.63 or 1.6288, something like that, just to make the computer happy. We'd normally round that down. We're normally not talking to a computer. All right. So that's the first step. That was step 1. We did that. We used the y direction and we got the time, and we're pretty happy about that. Next up, we got to do step 2, which was to use the x direction and get the distance. Okay, so I'm going to come in here. I'm going to use the same formula, but just the x direction version of it. On the cliff problems, I typically don't use either one of these. I usually do it in the y direction, this guy, and then do it in the x direction here. So let's write that down. X equals v naught xt plus 1/2 a sub xt squared. And I get lucky here when we haven't even pulled these yet, so I need to do that. But I need to fill in my x direction variables. What's happening in the x direction? Well, it's thrown horizontally at 6 meters per second. So it's all to the right. I've got a speed, and all that initial velocity is to the right. So that goes right here. I'm looking for the x, so that's another number that I have to deal with. A sub x here is 0. There's nothing speeding that rock's motion to the right, up, or down. It's not going to slow down or speed up. It's going to keep moving 6 meters per second to the right. Please don't put 9.8 right there. Gravity does not pull sideways. Gravity pulls down. It belongs over here in the y direction, not the x direction. Okay? It looks like we've only got 3 numbers, not enough. But remember, we just found out that this was 1.63 seconds. So I get to bring that over and fill in this, and now I've got 1, 2, 3, 4 numbers to work with, and I'm good to go. All right, first thing I do, a sub x equals 0. 1/2 times 0 times t squared is 0. This all goes up in smoke. I need to take the initial velocity, which was 6 meters per second. The time is 1.6288. I'm going to put a couple extra here. If you round off too much, you get something called round off error. So I like to round at the very end of all of this. And let me just go back and get that number after we hit that this thing. And it gave us the time. Right here, the easy thing to do is I just need to multiply that number by 6. It's still in the calculator. Just go times 6, and you'll get the whole thing. Then you can round that to wherever it would be. Normally it'd be about 9.8 to keep D2L and the computer happy. I might go down to there. Okay. So something like that. That's a cliff problem. All right. Those look like a lot of work. Once you've done a couple of them, they're not too bad. All right. It's the same formula twice. Just got to make sure you separate out the x and the y variables. All right. This is a little interesting thing here. I've also got a set of problems called the level ground problems. Level ground is anything that happens on level ground, right? There's some kind of object right there, and it goes up and it comes back down. It's a perfect parabola there. It's perfectly symmetric about the center line of this thing. And maybe we shoot a cannon, and the cannonball goes up and comes back down. Maybe we jump a bicycle. Maybe we throw a frisbee, kick a football, hit a golf ball, whatever the problem is. If the launch point and the landing point are at the same height, then we're going to call that a level ground problem. And we've got some formulas here that tell you how long it's going to spend in the air, how far out there it's going to land. This one's kind of nice if you want to say, well, I'm firing a bow and arrow, and I want to hit a target over here. What kind of angle do I need to aim that thing up at? Theta is the symbol that we use for angles. Comes from the Greek alphabet. And so that's an important part of this. You know that the higher you aim, then the farther it's going to go, right? Those are related. And this trig function right here, sine, is what ties all that together. You can't do this without trigonometry. So that's some really powerful mathematics, and I hope you get to appreciate it because it's good stuff. But the time in the air, how far does it go? What angle do I need to aim up at to hit a certain target r distance away if I'm firing at V0? V0 is the other variable here, and I got that kind of steep, but V0, theta, and r would be those 3 variables there. How far away, how fast is it going, and what's the angle. So let me show you how those work. Right here, a football is kicked at 8 meters per second at a 13-degree angle. They didn't say it's on a football field, but they sure didn't say it's on a cliff, right? So I'm going to assume this is a level ground problem, and I would come in here. Again, you're just looking for the numbers. There's a number, there's a number, there's a number. Okay? Since I'm looking for the range, I'm going to try using the range formula. You can see it down there at the bottom of the screen. Looks like that. And because I'm looking for R and I've got everybody else, this one's ready to go. I don't need to do any algebra on it. The initial velocity is 8 meters per second. Formula says I got to square that. I've got the sine of 2 times theta. Theta is 13 degrees. And then I've got g is 9.8 meters per second squared here. Now, I don't need to worry about positive or negative in these things, okay? G is always positive. Okay, just put in 9.8. If you go to the moon, I don't know if you know this, but one of the astronauts carried along a golf club and a golf ball, a couple golf balls, and practiced golf up on the moon. And he would have had to use a different G there. In general, the golf ball would go a whole lot farther because gravity's not pulling it down as much, right? And so a little interesting tidbit from history and whatnot. But we're ready to go on this one. So I'm going to come in here. I've got that 8. Don't forget to square it. Hit your sine button. Inside, you got to go 2 times 13. You could just say 26 degrees. And then I want to divide that by 9.8. Notice that I closed off the sine. That's something people forget to do. That will mess you up. When you hit sine, it starts a parenthesis. When you're done with what you want to take the sine of, you got to close it off and then do your division. So the range on this thing is 2.86 meters. Okay? Something like that. That's not very far. In this other problem, though, we've got a cannon. And check it out. It's going 428 meters per second, much faster. We're firing at a higher angle. So this thing is going to go way up in the sky and go way back down. It's going to go a super long way because it's a cannonball instead of just some little football. And it's going to spend more time in the air. That's what we're looking for. Got a formula for time right here. And you go T equals 2V naught C sine theta, just a single theta here, over G. And the V naught is 428 meters per second. Sine of 33, that's my angle theta. And I want to divide that by G, 9.8. Come in here and I go 2 times 428 sine 33, close that up, divide by 9.8, and it's going to be in the air for 47.6 seconds until it hits the ground. Maybe in D2L put 5.7, maybe in 5.73 or something, you know, but should be fine. And that's going to be in seconds. Cool? That's the level ground problem. Please do not mix that up with the cliff problem. If they tell you it's a cliff problem, they're going to come along and say there's a 13-meter fall off there, right? See how the level ground problem looking like this and time to go bonk? Like that's going to be a very small part of the whole thing. Cliff problem, you got to do it with the 2 steps. Level ground, just that 1 step right there. All right, now, I wanted to say a little bit about calculus. If you're in the Physics 221, then you need to know a little bit about calculus. If you're in 201 or physical science or something like that, and you don't need the calculus stuff, you can go to sleep for just a second here. Right after this, I'm going to bring up the whole list of everything and run through it one more time here. But for the last new thing here, let me tell you just a smidgen about calculus and how that works with kinematics. Calculus does 2 things really well. The first thing that it does really well is something called the derivative. And the derivative is useful to find slope. If I were to get in my car and go up a hill and back down the other side, you can see that my car would be pointing uphill. Right here it'd be pointing level. And right here I'd be going downhill. So the slope is up, positive. Over here the slope is down, negative. And at the top right there for just a second, I'm going level. The slope is 0. All right, calculus will find that for you. If you have a function of time, then you can use the derivative to say, well, go get me the slope at every point in time. And let me show you real quick what I'm talking about here. If I had a function of time like x equals 3t squared plus 2t minus 4, okay? See how it's got t's in there? That makes it a function of time. If you see one of these, you know you got yourself a function of time, and you can only do a couple of things here. One, you could plug in different values of time and say, well, at time equals 2 seconds, what's my position? Or I could take the derivative of it and get the velocity. Let me show you what that looks like. V equals the derivative of x with respect to t. In this case, I know that x is 3t squared plus 2t minus 4, and I just take the derivative of that. Here it's a real simple process. The derivative of polynomial would be the derivative of each of the terms, and I do this little funny thing where I take the exponent and multiply by the coefficient, so that would be 3 times 2 or 6t, and this goes from 2, drops down to the next one, 2 down to 1, so there's really a t to the first or just t there. I'll do the same thing right here. This is t to the first, so 1 times 2 would be 2. And t is going to drop from t to the first to t to the 0. T to the 0 is 1, so I just get that. This one's actually t to the 0 right here. 0 times 4 is 0. Okay, so you see how that last term just kind of disappeared. All right. The velocity of a particle that has a position given by this is going to be that at every point in time. And again, you could plug in whatever values of time there that you wanted to. So that's pretty handy. You could actually do it one more time and get the acceleration. And if I take the derivative of 6t plus 2, then I just get 6. Okay, it's always accelerating at 6. All right, so that's handy. On the other hand, I could go the other way and use this little funny mark, which is called the integral. And the integral is useful because it finds the area under a curve. Okay, if I have a function of time that looks like that, maybe this represents me riding to the park and then to the store, something like that. And my velocity is changing like you see here. I'm riding pretty slow, I speed up, slow down, I go backwards to the store. If I want to know the distance that I've traveled, it's everything that's underneath this curve. The total effect of all of that is what's underneath that curve. Maybe this is the stock market and it goes up and it comes back down. If you want to know the total amount of money that a company made, then you could add up all of those little pieces under there. The area under the curve would do that. So since I've got a velocity right here, let's take that one and we'll integrate it. We'll say x equals the integral of v with respect to t. And in this case, we know that that velocity is 6t plus 2. And I want to integrate that with respect to t, which is all that little notation means right there. When I do the integral, it's a polynomial, so again, it's just term by term. And I take the 6t. Remember how this went down from 2 to 1? Right there. Well, now I got to go backwards. So instead of 1, I got to go up to 2. And then remember how we multiplied the exponent by the coefficient? The opposite of that would be to divide by the new coefficient. I could do it here as well. This is really 2 to the 0. Bump that up to a 2. Divide by the new exponent. And then you can see that that much, 6 divided by 2 would give me the 3t squared. That's what we had at the beginning. Right here, 2t over 1, that's just 2t. That's what we had right there. But, I guess I should have done it up here. There's this negative 4 that disappeared that turned into a big 0 right there. So what we do is we add a constant of integration. There are ways to find that number, but that would be the integration, and you could find that. Again, If you're in 201, if you're in physical science, you don't need to worry about any of that. But hopefully you get a little appreciation for calculus and go, man, I got to go get me some of that, because that looks like good stuff. It is good stuff. Okay. Here's that summary that I promised you real quick. You got 5 variables. That's all. We're talking about measuring 5 numbers. And then we've got 3 ways that link those together. Every problem you're going to want to box it up. It's like a little, like the old letterbox thing, at the post office. And the postman stands there and says, this is a letter from Mr. Jones, and he throws it in the top box. Well, if it's, X, and you got an X, you throw it in the top box, right? You're just going to fill up as many of those as you can. You're going to figure out which ones you know here. And if it looks like that, you could solve this for V naught. Maybe that's what you want. Okay? Pick the right formula based on which ones you have over here. All right, if you got X and V and A and they want T, X, V, oh, you know what, I should have put that here. Okay, we'd have to do something else for the other one. X, V naught, A, T, X, V naught, A, T, okay? And we'd use that second one. It's just a little matching game right there. If it's a cliff problem, you got to separate the X and the Y directions. It's 2 different kinematics problems. In physics, if it's a 2-dimensional problem, you separate it. What's happening in X, what's happening in Y, and then you put it back together. You're going to use the displacement formula. That's this one that is already circled. You're going to do it usually in the Y direction to find time, and then the X direction to find X. Not always, but almost always. You got the level ground special case problems here. Time in the air, how far does it go, what angle do I need to aim at to hit something a distance away. And then maybe there's a calculus, again, that only works with functions of time. So if the problem just gives you numbers, you can't do this anyway. But if you've got a function of time in there, something like v equals 3t squared plus 4 or something like that, that's a function of time. So you could integrate or take the derivative to get to somewhere else. Well, good. Thanks for stopping by today. That's kinematics in a nutshell. And we will work a bunch of these in class. So get busy on the LOPs. Do lots of examples of these. And I do want you to bring all your questions and let's work through them. So thanks for stopping by. Have a good one.